Okay, this is for Physics 5B Summer 2020. It's August 6th, 2020, about 8:53 p.m. Just wanted to show this. Okay, so the course modules. So what's new here is, there's a place to turn in homework number 6. So there's worksheet number 7. I didn't put a place to turn it in because the solutions are on it this time on purpose. So I'm not going to have you turn the rest of it. I'm just going to put the solutions on the papers the rest of the semester. And then document chapter 22. So that would look like this. Chapter 22, you got some equations here that might come in handy. And then the online number 7 is this guy right here. I got the solutions on there if you haven't downloaded it already. Okay, then you got the homework. I think there's not going to be any homework in chapter 22. I think we're just going to go to chapter 23 now. All right, and then PowerPoint. So PowerPoint is this guy right here. That's the newest PowerPoint. It's up. It is right someplace. There. I just uploaded it just now. It's the newer one. If you downloaded one already this morning or Thursday morning, this is got more stuff in it. All right, so let's go over to the PowerPoint. All right, so magnets. We're talking about magnets, chapter 22. And naturally occurring lodestone attracts iron. That's how ancient people first discovered magnetism. They got this naturally occurring rock, and this naturally occurring rock was attracting iron. So it's like a magical thing to them, okay? And then, but it took centuries till people actually started studying it in depth. So pieces of lodestone could be shaped easily to align in the Earth's magnetic field, making navigation more accurate. So they actually were able to, if they had some concept of north and south, and they realized wherever they went, the compass needle was always pointing in this one direction. They had an idea what direction that always was, no matter where they were. Magnets are strongly attracted to most unmagnetized materials, so metals. So like iron, a lot of the metals. Aluminum is very weak magnetically. Lodestone attracting iron is how magnetism was first discovered, possibly thousands of years ago. Magnets can be attracted or repelled by other magnets. Okay, so once you magnetize a piece of iron, then it can be repelled and attracted either way. Then you got your refrigerator magnet sticking to your refrigerator. Okay, I just skipped one, didn't I? Okay, magnets have a north and south pole. Unlike poles attract, north repels north but attracts south. South repels south but attracts north. So it's just like unlike charges attract, like charges repel, electron repels electron but attracts a proton, proton repels a proton but attracts electron. So unlikes attract, opposites attract, but sames repel. Okay, due to the molten core full of positive iron ions and negative free electrons, and the rapid rotation of the Earth, we are surrounded by a strong and vast magnetic field. Down here, there's this molten core. It's way deep inside the Earth's interior. Okay, way down there. And it's basically got a lot of positively charged iron ions, and it's got a lot of electrons that are free. And if you want to get a magnetic field, what you need to do is have a charge in motion. Charge in motion causes a magnetic field. So Earth's got the charges, and it's got the motion because Earth is going to rotate once on its axis every 24 hours. So like here you are in Sacramento, 12 hours from now, as seen from the sun, you'll be over here where Siberia is or someplace like that. And then 24 hours from now, you'll be back here, back where the sun will see in the same place. But you went all the way around like this in 24 hours, as seen from the sun. That's rapid rotation. So you've got charge in motion, and then you've got the charge in motion, you've got the magnetic field. One way to model this magnetic field is to think of a giant bar magnet stretching from near the south geographical pole to near the north geographical pole. So these don't line up exactly with the geographical poles. Right now the south geographical pole is near the north. Right now the south magnetic pole is near the north geographical pole, okay? And the north magnetic pole is actually near the south geographical pole. And they switch, but it's a long time between switches, okay? Many thousands of years. But we know that by studying lava rock that solidified at different times, so we can see what the magnetic field that was dominant at the time had to be because of the way that the lava rock solidified. So we know it switches and it moves around. They go up there every year, try to measuring where is the magnetic field now, the Earth's magnetic field now, because it moves around. And it could switch. We don't know why it switches, but it could switch. If it switches in our lifetime, who knows what it would do to all sorts of electronic gear and all sorts of things. It just we don't know. Like we didn't know, like back in March, that a virus was going to like cause havoc. Maybe the switching of the magnetic poles could cause havoc someday. Who knows? As of now, though, the south magnetic pole is near the north geographical pole, and the north geographical pole is near the south geographical pole, and the north magnetic pole is near the south geographical pole. This is why the north pole of a compass needle points in the direction of the north geographical pole. It is actually being attracted towards the south magnetic pole. So if you're down here in Sacramento, it's pretty accurate. It's going to point up there. You get up here close, though, you say, whoa, what's going on here? It's pointing this way, but I think the north geographical pole is this way. Well, it's being attracted to this guy. So it won't lead you right to the north geographical pole. If you get too close, it'll lead you away from it, as a matter of fact. Okay, the poles always come in pairs. If you break a magnet in half, you get another north-south pair. That's what we're doing here in this picture. You've got your whole magnet, you've got your south pole, you've got your north pole. You break this in half, south-north, south-north. You just got two magnets with the two poles. You break these two in half, you just got four magnets. So you keep breaking, and pretty soon you get down to the iron atom, for example. So here's the nucleus, and you got the electrons moving around, you got the south pole and the north pole here. So you go down further than that, you get down to quarks. All right, ferromagnets and electromagnets. Ferromagnets materials are materials such as iron that can be turned into permanent magnets through ferromagnetism. Ferromagnetism. Place iron in a strong magnetic field. Once you place it in the strong magnetic field, it magnetizes a little bit. You heat it, and then that thermal energy causes it to go all the way and become pretty much a strong magnet, okay? And the iron becomes magnetized. The iron south pole forms at the north side. So here, you got the north side here. That's the side the south forms it right here. North-south, you got south-north, okay? So the south side is going to, because south attracts to north, the south side is going to be forming on the north side of the magnetic field. The north side is attracted towards south. It's going to form on the south side of the magnetic field. Now, what is in here are these little domains. Okay, remember I said charge in motion, magnetic field. Well, electrons spinning on their axis, that's charge in motion, and that's what contributes the most to these magnetic fields. So here you got this domain right here where the electrons are spinning such so that the direction of the field is in this direction. But here it's in this direction. Here it's in this direction. Here it's in this direction. Here it's in the opposite direction as this guy. So some of these guys are actually going to cancel these guys out. So there is no net magnetic field. You may have a little net magnetic field in this one little domain here, but overall there is no net magnetic field. Now you stick it in the magnetic field, then we start to get a little bit of a kind of a weaker magnetic field. See, these guys are sort of pointing almost in the same direction. This guy's not pointing in the right direction at all. But these guys kind of merged here and became this bigger one. It points in that direction, that direction, that direction. This guy's kind of pointing off that way and so on. Then we heat it. Then we do the heat. Then we heat it right here. Okay, and then once we heat it, then we put thermal energy in it. Then it becomes a permanent magnet with a south side and a north side. Ferromagnets and electromagnets. Okay, in the early 1800s, it was discovered that electrical currents, the flow of charge, also creates a magnetic field. So now we're talking about magnets causing a magnetic field, refrigerator magnets, bar magnets, horseshoe magnets, and so on. But they discovered, wait a second, a current, flowing charge, that also causes a magnetic field. And basically there was a great story that used to go along with this, that Ørsted, the guy who discovered it, he was messing around with his little magnetism stuff, and nearby another famous scientist from way back, his name escapes me at the moment, had current going, and then Ørsted just happened by accident to knock his compass near the other guy's wire of current, and noticed that, oh, it had an effect on the compass needle. And apparently that story isn't true according to Wikipedia. That Ørsted was already working on this and knew about the fact that a current causes a magnetic field already. If a compass is placed isolated on a table, it will align itself in the Earth's magnetic field. Place a current-carrying wire near the compass And if the current is large enough, the compass needle will align itself with the magnetic field generated by the current instead. All right, so if there's no current going through here, it's going to align itself with the Earth's magnetic field. Put a current through there, it's enough current to create a magnetic field stronger than what it is localized from the Earth here. It'll actually react to the magnetic field generated by the current instead of from the Earth. Okay, so where is this used every day? Well, remember, you could turn current off and on. So you turn current on, you've got a magnet. You got a magnetic field and a magnetic force. You turn the current off, the magnetic force goes away. And you put like iron or something in there. There's certain metals that will go magnetized when they got a current running around them and unmagnetized when there's no current running around them. So basically, if there's a magnetic field, you can pick stuff up due to magnetic force, different types of metals. And there's no magnetic field, and you just drop the stuff. So you turn on the current, you pick up all this stuff out of this metal scrap yard, whatever this is, and then you can move it to where it's supposed to be. You turn the current off, magnetic field goes off, and all that stuff falls where it's supposed to be. That's how they do with cars. You ever seen one of these things pick up a big car, turn the current on, pick up the car, get the car to where it's supposed to be, turn the current off, and then drop the car. In scrap metal yards or car wrecking yards, the electromagnet can be used to pick up metals when the magnet is on, and when you want to drop the metal, simply cut the current to turn off the magnetic force. Okay, ferromagnetism. Okay, so iron filings align themselves in the local magnetic field if it is strong enough. So over here, you've got comparison pictures. These are iron filings, okay? They're not magnetized, but they react to the magnetic field anyway. What will happen is you get the magnetic field lines going like this. You can kind of see the pattern here. These are the magnetic field lines, and the magnetic field lines for the coil, this is a coil here, you've got these coils going in and out of this paper or whatever this is, and you got the magnetic field lines on top. So the magnetic field lines around the coil look very, very much like the magnetic field lines around the magnet, okay? The magnetic field lines seen by following the iron filings look extremely similar when comparing the geometry of the field generated by the current carrying coil and the one generated by the bar magnet. Okay, let me take a break for a second. Okay, so magnetic fields and magnetic field lines. Okay, just as with the gravitational field and an electric field, we can map out a magnetic field, and we can do that by placing compasses. Now, compasses don't tell you the magnetic force acting on them, but they will tell you the direction of the field. You can see they're leaving north. Remember that the north side of the compass needle will be repelled by north, and then we'll follow this line towards the south. Same on both sides. And we just kind of make a solid line. We fill in the gaps. We know what the line's going to look like. We just complete this, and this is what we get. And then we can surmise that if we're coming out this side and going in this side, that we can just complete it with the with what's inside the magnet itself. Okay, place compasses in this field, and the path and the north pole will point towards the south. Follow the compass needles with a solid line, and we see the shape of the magnetic field. You can see then what the field would look like inside the magnet itself over here. Okay, did I skip one? No. Magnetic fields, okay, and a hard and fast rule summarizing the properties of magnetic field lines. The direction of the magnetic field is tangent to the field line at any point in space. A small compass will point in the direction of the field line, just like we have up here. Okay, it's pointing the direction. The direction is out of north and into south. The strength of the field is proportional to the closeness of the lines. Okay, we go back up here. The iron filings are doing a really good job. Look at how dense they are inside this coil. So the field is very strong out here. Okay, and it's not so strong here, but it's stronger over here. Okay, so that gives us an idea. Okay, the strength of the field is proportional to the closeness of the lines. It is exactly proportional to the number of lines per unit area perpendicular to the lines, called the, I don't know what that is, that must be a misprint or something, areal density, called the areal density. Magnetic field lines can never cross, meaning that the field is unique at any point in space. They're never crossing. We can see the actual field lines here. They don't cross anywhere, okay? They're not crossing. Magnetic field lines are continuous, forming closed loops without beginning or end. They go from North Pole to South Pole. So here we can see in their continuous loop if we look inside the magnet as well. Magnetic field strength, force on a moving charge in a magnetic field. So here's our equation. You have a particle in a magnetic field, okay? It's just a simple charge, an electron, a proton, whatever. And they're treating these like they're positive charges for the first part. But force on that charge, the magnetic force on that charge will be equal to Q, that's the charge itself, times the velocity. So that how fast the particle is moving, that's important. Then the strength of the magnetic field, and then this is the angle between the magnetic field and the velocity. Okay, F is I got this boldface because F is a vector, where F is the magnetic force in newtons. Q is not a vector, it's a scalar, is the charge of the particle in coulombs. V is a vector, velocity is a vector. V is the velocity of the particle in meters per second. Then B also is a vector, it has direction associated with it. We see that up here. It's got a direction. Okay, so it's a vector. It's got a magnitude and a direction. B is the strength of the magnetic field. We can call it B field from now on. And it's going to be in Teslas. And theta is the angle between the B field and the velocity, both vector quantities, and we get another vector force. If the B field and the velocity are perpendicular to one another, then sine of theta equals sine of 90 degrees, which is 1. So that's when you're going to have the greatest force, is when those two are actually perpendicular to each other. In this case, we would have the force equals QVB, and then the sine theta just became 1. So just QVB. Okay, the unit for magnetic field strength B is the Tesla, named after Nikolai Tesla. I think the car company's named after him too. Brilliant, brilliant scientist. Maybe just one level down from Einstein and Newton. Okay, we got this right-hand rule deal here. Magnetic field strength, force on a moving charge in a magnetic field. Okay, the right-hand rule. Point your fingers in the direction of the magnetic field. So there you got your fingers pointed in the direction of the magnetic field. And your thumb in the direction of the velocity. So your thumb's in the direction of the velocity. Okay, the force then shoots out of your palm. I didn't notice it. This is the second time I'm doing this. I didn't notice I forgot the then in there. Oh well. Just you can add to it, then shoots out, should be then shoots out from your palm for a positive charge. So we're picking a positive charge here, okay? If it's a negative charge, the force would be in the opposite direction. You can use your left hand in that case. But anyway, we're going positive charge. The magnetic force is perpendicular to the plane of velocity and magnetic field. So velocity and magnetic field, those two vectors form a plane, and the force is going to be perpendicular to that plane. Okay. The diagram shows the direction of the force if the moving charge is positive. Okay, if the moving charge is negative, the force would be in the opposite direction. Okay. And then we can do this guy. Make this bigger, I guess. All right. So we want to know the direction of the resulting force if we have these guys here. Now here's the thing. These guys here, think of an arrow, okay? If the arrow's coming at you, you see the point of the arrow. So you see this little dot. That's like the point of the arrow. If the arrow's moving away from you, then you see the feathers or whatever, the quill is it called, the back of the arrow. So if you see the dot, that means coming towards you. If you see the X, that means going away from you. So the magnetic field, the B field, is going towards you. So you point your fingers towards you. Okay, now you're using your right hand, and you've got to point your fingers in the direction of the velocity. The velocity is going down. So you've got your fingers pointing towards you, and you've got to move your hand so your thumb is pointing down. So if you do that with your right hand, and the force coming out of your palm, it's going to be going in this direction. It's going to be going left or west. Okay, they use west. If you look at a map, California is towards the west, the left coast they call it, the west coast. And then you got the other side, which would be the east coast, which would be to the right as you're looking at a map, say, of the United States. Okay, in this middle one, we got the magnetic field lines going to the right. So if you take your right hand, you move your fingers pointing towards your right as you look at the screen. And then your thumb has to be pointing up towards the ceiling. And that means that your palm is actually pointing towards the screen. So now the force would be into the screen. Okay, on this one here, the magnetic field's going out into the screen. So the magnetic field's into the screen. Point your fingers into the screen. Now the velocity is going to the right. So you got to turn your hand. So you got your fingers going towards the screen. You got your thumb going to your right. And now your palm is pointing towards the ceiling. So that's how we get that. Okay, this one here, you can't even do it. You'd have to dislocate your thumb to do this one. You'd have to injure yourself to do this one. You can't do that one. But look, they're parallel. That would be sine of 180 degrees. That's the same as the sine of 0 degrees. That'd be 0. So there is no force in this case. Okay? This one here, we've got the currents now going away from you. So you've got to point your thumb into the screen. You've got the magnetic field lines going up. So point your fingers towards the ceiling. Then move so your thumb is pointing into the screen, towards your screen, and now your force is going towards your right. Now the velocity is going towards you, so you point your thumb at you. You got to have your fingers going towards your left, and now we're going down. Okay, we're going down. Okay. Now, this guy here, so we don't get confused, this is for a negative particle, okay? See, if you did this for a positive particle, the magnetic field lines are going into the screen. So you put your fingers so that they're pointed towards the screen. Then you have, say, this velocity right here, okay? This velocity right here. So you turn your hand so your fingers are going into the screen, and your thumb is pointing in this direction here. Well, that would give you a force based on what we just did going this way. But remember, if it's a negative, the force is in the opposite direction. That's why they show the force going this way. You could use your left hand. Put your fingers, use your left hand, put your fingers like you're going into the page, point your thumb in the direction of velocity here, like we just did, darn it, like we just did, and now where's your palm going? It's going in that direction, and it'll do the same thing all the way around. So what this means is, this is a centrifugal force, okay? It's just like it's a centrifugal force, just like the force of gravity becomes a centrifugal force when it's the gravitational force of the sun keeping the Earth in orbit, or it's the gravitational force of the Earth keeping the moon in orbit, or you're swinging a can or a rock over your head at the end of the string, then the tension is the centrifugal force. Here, the magnetic force is the centrifugal force. So note that in this case, the charge in motion is negative. That is why the force is in the opposite direction than shown in the slide above. That was for a positive charge. Here the magnetic field is into the page. The X here is the back of the arrow moving away from you. The particle is trying to move in a straight line along a plane of the page. So the particle wants to do this. It wants to go off straight. What's keeping it from going off straight? The magnetic force is what's keeping it from going off straight. The particle is, the particle is trying to move in a straight line along the plane of the page, but like the gravitational force keeping the Earth in circular motion around the sun, the magnetic force keeps the charged particle in circular motion as well. All right, because magnetic field B and V are perpendicular to each other, we have F equals QVB. So in other words, in this case, we don't have to worry about the sine theta. But Newton's law, F equals ma. Force equals mass times acceleration. Since the particle is kept in circular motion by the centrifugal force we have for the acceleration, remember this goes back to your 5A days. You thought you were done with those days? Nope, they're cropping up. They're just as useful now as they were back then. Acceleration equals velocity squared over radius, the radius of curvature, obviously. Therefore, this little symbol means therefore. I always liked it. Force equals QVB equals ma, and I just put the A, this here, in this A here, in for A, so we get V squared over R. Solve it for R. R is going to be equal to the mass of the particle times the velocity of the particles moving, divided by the charge of the particle times the magnetic field. R is the radius of the circular motion of the charged particle. Okay, and then here you got force on moving charge and a magnetic field examples and applications. The solar wind is made up of charged particles expelled by the sun. These are very high energy particles that if they were able to reach the Earth in any large amount, they could do serious damage to living organisms on the Earth, including human beings, including little doggies and little kitties and all sorts of things. They do horrible, mean stuff. But they get trapped in the magnetic field that surrounds the Earth. So these charged particles, such as protons and electrons, as the diagram in the previous slide showed, as in the diagram in the previous slide, these charged particles can get trapped in circular motion around magnetic field lines. Okay, they're getting trapped there. Okay, they're not zinging us, hitting the Earth and killing us. They're getting trapped in the magnetic field. This leads to the aurora borealis, the northern lights in the northern hemisphere, and the aurora australis in the southern hemisphere. So we get those cool looking lights at night. Okay, we can do a problem, I think, maybe a couple of problems now. Let's see. Okay, what is the maximum? Yeah. Okay, what is the maximum force on an aluminum rod with a 0.100 microcoulomb charge that you pass between poles of a 1.50 Tesla permanent magnet at a speed of 5 meters per second? Okay, so here you've got the force. You got this guy here. It's going to be maximum force because they're perpendicular. I think they're asking for maximum force. So maximum force comes only when sine theta is equal to 1. Otherwise, it's less than that value. So you get rid of the sine theta. You got QVB. So he gave you the charge. That's 0.1 microcoulombs. There you are right there. You got the velocity of 5 meters per second. There you are right there. And you got the 1.50 Teslas. You got that right there. So the force that particle would feel, the maximum force on a 0.100 microcoulomb charge that passes through a 1.50 Tesla magnetic field at 5 meters per second would feel a force of 7.50 times 10 to the minus 7 newtons. Okay, an electron moving at 4.00 times 10 to the third meters per second in a 2.50 Tesla magnetic field experiences a magnetic force of 1.40 times 10 to the minus 16 newtons. What angle does the velocity of the electron make with the magnetic field? And there are two possible answers. All right, so okay, I'm back. We were looking at this page over here. Okay, so basically what you do here is you got your force equals QVB sine theta. So you solve for theta. Theta is going to be equal to the arc sine of all this stuff here. So then arc sine, you plug in your numbers and you get 10.1 degrees, or theta equals 180 degrees minus 10.1 degrees, you get 169.9 degrees. So if you plugged either one of those into this equation for sine theta, both times you would get 1.4 times 10 to the minus 16 newtons. Okay, this one here is, I guess we can do this one here. It's only number 11 in your own. A physicist performing a sensitive measurement wants to limit the magnetic force on a moving charge in her equipment to less than 1.00 times 10 to the minus 12 newtons. What is the greatest the charge can be if it moves at a maximum speed of 30 meters per second in the Earth's field? Discuss whether this would be difficult to limit. Okay, so according to your own, the maximum strength of the Earth's magnetic field is 5.00 times 10 to the minus 5. You can also Google that. Okay, so you got force equals QVB sine theta, but for maximum force, you're only going to get that when sine of theta equals 1. Okay, so that's why that's there. So you got F equals QVB. So you solve for Q. Okay, so the physicist performing a sensitive experiment wants to limit the magnetic force on a moving charge in her equipment to less than that many newtons. Okay, what is the greatest the charge? So she's got to find the charge that can be the most. And if you go over that charge, then who knows? You're in trouble. You destroy the equipment. I'm not sure. All right, so you got the force, which they gave you is right here, 1.00 times 10 to the minus 12 newtons. You've got the speed being 30 meters per second. There it is right there, 30 meters per second. You've got the magnetic field, which is the Earth's magnetic field, 5.00 times 10 to the minus 5th, according to your own end. I think if you look up on Google, it'll say the same thing. You get 6.67 times 10 to the minus 10 coulombs. Okay, that's pretty small. Okay, common static electricity involves charges ranging from nanocoulombs to microcoulombs, which are much bigger than what she got there. Nanocoulombs would be 10 to the minus 9. This is 10 to the minus 10, but microcoulombs, that's 10 to the minus 6. It's thousands of times, that's 1,000 times bigger, more than 1,000 times bigger. Therefore, it would be seen to be difficult to limit the charge to less than the value found in Part A because the charge is smaller than a typical static electricity. So she'd have to figure out some way to get rid of all static electricity in order to be able to actually do this properly, if that's what she wants. Okay, can we do this one? Yes. No. Yes, we got that. That's the equation we just got a little bit ago. Isn't it? Yeah, there it is. Okay, there it is right there. All right. Okay, so the cosmic ray electron, that's an electron now, so we know the charge. Cosmic ray electron moves at 7.50 times 10 to the 6th meters per second, very fast. Remember, speed of light moves at 3 times 10 to the 8th meters per second. Perpendicular to the Earth's magnetic field at an altitude where the field strength is 1.00 times 10 to the minus 5 teslas. So this is way up there. Remember, at the Earth's surface, we had the 5.00 times 10 to the 5th, but up there, where this cosmic ray is, it's only 1 times 10 to the minus 5th. It's 5 times less. What is the radius of the circular path the electron follows? So it gets trapped in the Van Allen belt. It gets trapped in the magnetic field. So basically, in this case, the magnetic force is a centrifugal force, and we just kind of go back with QVB equals mv squared over r. The v's will cancel out. Well, this v will cancel out with one of those v's. Okay, that's what happens there. And we solve for r. We still got the v, both v's there. So r equals v squared over v here. So that's going to cancel out. So we get mv divided by qb. This is the mass of the electron. Okay, so you have to look that up. This is the speed they gave us. This is the charge on the electron. We're dropping the minus sign. And then this is the field. Okay, there's the field that we were given. And we get 4.26 meters. That would be the radius. So you can imagine 4.26 meters. That's the radius that this cosmic electron would be spinning at that radius in the magnetic field. Okay, I guess we can do this one too. An oxygen-16 ion with a mass of 2.66 times 10 to the minus 6 kilograms travels at 5.00 times 10 to the 6 meters per second, perpendicular to a 1.20 Tesla magnetic field. Okay, well, perpendicular means the velocity is perpendicular to the field, which means we got sine theta equals 1 again, which makes it move at a circular arc with a radius of 0.231 meters. Okay, with a 0.231 meter radius. What positive charge is on the ion? What is the ratio of this charge to the charge of an electron? So see, this is an ion. So what you do is it's a positive. So you've taken electrons off, more than likely. You've removed electrons, I'm supposing, or you could have added electrons. Either way, you've made it an ion. All right. So what positive charge is on this ion? So here we got the same old equation we just used. Right here, this R equals mv over qb. Solve it for q. That'll be the charge that this oxygen-16 ion has. mv, the mass of the ion, times the velocity. Okay, divided by rb. So we've got the mass. They gave it to us up here. We've got the velocity. They gave it to us over here. We've got the radius. They gave that to us right here. And then 1.2 teslas. They gave that to us right here. We get 2.80 times 10 to the minus 19 coulombs. Okay, so what is the ratio of this charge to the charge of an electron? Well, just take your 4.8 times 10 to the minus 19 coulombs, divide by 1.6 times 10 to the minus 19 coulombs, you get 3. Okay, so with the 3, it's an integer. Do we expect an integer? Yeah, because every time you take off an electron, you're taking off 1.6 times 10 to the minus 19 coulombs, or you're adding 1.6 times 10 to the minus 19 coulombs. So this number is always going to be some integer multiplied by the electron charge to get it. So yeah. Okay, so let's go on here. Can we do this one? No. Cannot do this one yet, I don't think. No. All right, so back to here. We are here. Okay, magnetic force on a current carrying conductor. Here, instead of a single charge, all the ones we just did were for a single charge, moving through a magnetic field, you have a current moving through a magnetic field. So now you've got a wire, a current moving through there. Okay? Now in this case, the force is going to be equal to the current, I, times the length of the wire that's in the magnetic field, times the magnetic field itself, times the sine of theta. Okay? I is the current in amps, L is the length of the wire in the magnetic field, and theta is the angle between the magnetic field and the direction of the conventional current. So we're using conventional current. Conventional current flow is opposite of electron current flow. That means we can think of it as the positive that's moving actually. If the current and the magnetic field are perpendicular, then we have F equals the current times the length of the wire inside the magnetic field times the magnetic field itself, right here, down here. Another right-hand rule. Okay, so, but it's just like the other one. Instead of pointing our thumb in the direction that the particle is moving, velocity, we point it in the direction of the current. So everything's the same. If you understand the other one, this one's the same thing. You point your finger in the direction that the current's moving. You put your thumb in the direction of the current, the conventional current. You put your fingers in the direction of the magnetic field, and out of your palm pops the force. The right-hand rule is pretty much the same as it was for the charged particle. Conventional current flow is used as the direction of the current. Conventional current flow is opposite electron current flow, so it can be thought of as the flow of positive charge, even though it's just positive because the electrons are going the opposite direction. Torque on a current loop, motors and meters. Place a loop in a magnetic field. Flip a switch so that current flows through the loop. The magnetic field then exerts a force on the loop, causing it to turn. Okay, so you got this magnetic field. You got these two magnets here. So this could be like the top of a horseshoe magnet, for example. Okay, and you put this coil in there. Now, at first, nothing happens, but the instant you put current through there, you're going to get forces acting on this coil that get it to rotate. Okay, so we're converting electrical energy into mechanical energy. Okay, this is better known as an electric motor. You just made an electric motor. We're taking electrical energy. That's where the current's coming from. You got to hook this up to some power source. That's the electrical source. But when we put the current through there, this thing starts spinning. Well, now we just turn the electrical energy into mechanical energy. And here's some diagrams that kind of show you what's going on. It's a little bit confusing, but see, here's the thing. Okay, it's actually, the forces are actually acting on this guy and this guy. The vertical forces, the force, if we did the right-hand rule, okay, you got your fingers pointing in the direction of the magnetic field, your thumbs pointing in the direction the current's flowing, you would get, this guy's force would be up like this guy's force would be down like that. They would cancel each other, okay? There is no force from these guys. So we have to worry about are these guys, this guy and this guy. And now while this guy feels a force, see, it's like a torque. That's what we're calling it. We're calling it a torque. Okay, it's like you got a box, you want to flip the box over, and so you get on one side, push at the top, your friend gets on the other side, pushes at the bottom, and then it's going to fall over on your friend because you applied a force at the top, friend applied a force at the bottom, you put a torque on the box, and it went over. Same thing's going on here. You apply a force in one direction on one side, in the opposite direction on the other side, that's going to cause it to spin. That's a torque, okay? And this is just going through, I was going to go through this in detail, but I don't want to, it's you can study, I got this right out of your book. See, right here, there's going to be no force because this right here, this line right here, just so you understand, this line right here represents these sides right here. Okay, and the reason you got the W over 2 is because it's this is like the central point right here. There's your W. So it's W over 2 is this distance from here to here, or from here to here. Okay, from the middle. So it's the width divided by 2 is how far the force is being applied from the axis of rotation. Okay. Oops, I didn't mean to do that. All right. So let's not. I mean, I've already been on here. God, I think I've been on here close to 50 minutes. Oh boy. 22.8 torque on a current loop. Motors and meters. This is the final equation for the torque on a single loop. The torque will be equal to, you got that width thing there, times the current times the length L. That's the length of this guy. See, there's the L right there. The length. Remember, it's the length of the wire that's in the magnetic field that's important. So the length there, it shows up right there. Times, obviously, the strength of the magnetic field, sine theta. Okay, then we can do a few things with it. So finally, we can do this with it. We get torque equals IAB sine theta, where I is the current and A is the area of the loop. Okay, I'm starting to lose my voice. If instead of one loop we have n loops, the equation becomes tau equals NIAB sine theta. Okay, now we can understand how the galvanometer worked. What you did was, well, you didn't do it, unfortunately, because we're not doing labs where you're getting your hands on stuff. But you put a current in here, okay, and that causes the needle, that causes this thing to spin. So you see, you got this guy hooked up to a needle, so there's your scale. This could be like current in amps, milliamps, could be volts, voltage in volts or whatever. And depending on how much current goes through here, this thing, you got a spring here though also, you got a spring. So to compress the spring, you need a greater torque acting on this guy. So you put the current through there, you put a torque on them, and then it pushes the spring, but then obviously the spring pushes back. So you compress the spring, and depending on how much torque you have on there, the more spring you can compress, and the farther up the needle will go. So this is how a galvanometer works. We can now understand how the galvanometer worked. A coil, the one with the small resistance R, which was usually about 25 ohms. Remember that? I think that's earlier this week, or I don't know, lose track of time. Is placed in the magnetic field. When a current flows through the coil, there is then a magnetic force on the coil, and the coil connected to the needle turns. In this case, the coil is not allowed to spin freely, but instead compresses the spring. If the current stays constant, then the force on the coil, the torque on the coil should be probably, the torque on the coil stays constant, and the needle stays on the same number. Okay, that's how the galvanometer worked. All right, this is 22.9. This is a good place to call it quits. All right, I'll try to put up another video tomorrow that'll finish off. Wait, what problems did we not do? Darn, I'll go back and watch the video to see what problems I didn't do. There's probably more, but this has already been a long video, and I'm starting to lose it. So let me call it quits now. I'll say good night, and I'll talk to you tomorrow. Good night.